In this video, we are starting our section on factoring, and our goals are to factor expressions that have 2 terms, 3 terms, and 4 or more terms. So in this video, we are going to talk about what factoring is, some common factoring formulas, and how we factor 2-term expressions. Okay, so what does it mean for an object to be factored? Well, when I can write it as a product of 2 or more factors, and usually those have to be simpler and smaller things than what we started with, then we call the thing factored. So for example, I can write 21 as 3 times 7. And those are smaller and simpler than what I started with. So this is called a factorization. In fact, I noticed that 3 and 7 are both primes, so I can't really split this up further. So that I would call this fully factored. But whereas when I write 99 as 10 times 10 minus 1, that's not factored because even though I have a couple of things getting multiplied together, well, then it's getting subtracted by the 1. And that's not allowed in this definition. It just needs to be like something times something times something. Like all the things need to be multiplied together. So the minus 1 doesn't fit into that mold. A similar type of explanation can be applied when I'm talking about expressions, like things that have variables. So for example, in part A here, both of these terms have an x squared in common. So I can factor that out. And then when I divide the first term by x squared, it leaves me with x. When I divide the next one by x squared, it leaves me with a minus 6. I could check that this works out to what I started with by just distributing the x squared back in. And if I do that, I do get what I started with. And this thing is factored because I've now written it in a form where I have something times something else. It's just a product of these smaller, simpler factors. But B, we factored out a common x from the first 2 terms. So I do have a product here, but then I have this extra plus 24, which means it's not factored. This is not factored. If instead it had been like something times something times something, like if everything was multiplied together, then it would have been factored. So later in the section, we'll see, well, how do we actually factor something like this? This is what's called a quadratic. Okay, so next up, let's talk about some common factoring formulas. So difference of squares. We would have seen this in our last section. If difference means subtraction, I'm subtracting 2 perfect squares. That factors as x minus y times x plus y. I could verify this by foiling it out. If I FOIL it all out, I should get this. We also have a formula for the difference of 2 perfect cubes. It starts off in a very similar way, but the second parentheses has x squared plus xy plus y squared. I can also verify this by foiling this whole right side out. We'll get a bunch of cancellation, and you'll just be left with x cubed minus y cubed. So a sum of cubes also factors. There's actually a very quick way to get that if I already have my difference of cubes, which is we plug negative y into y. So anywhere I see a y on either side, I'm going to be plugging in negative y instead. So on the left-hand side, I would get x cubed, and then minus, instead of y cubed, I would now get negative y getting cubed. And on the other side, on the right side, I would get x minus, instead of y, I would write negative y. I'd write negative y. And then I'd get x squared plus x times, instead of y, I'd write negative y. And then finally, plus, instead of y squared, I would be writing negative y getting squared. So if I were to simplify this, well, the x minus negative y, that double negative becomes a positive, and I get this left-hand side. Oops, sorry. I'm looking at the wrong thing. So, sorry, let me go back to this. If I do a negative and I cube it, it's going to be negative. And this other negative now makes it positive. So this whole thing will give me a positive. On the right-hand side, well, this double negative also gives me a positive. So let's write that. On the right-hand side, I would get x plus y. And then the second parentheses becomes x squared. And then minus xy. And then plus a negative getting squared becomes positive. So I get plus y squared. And that's my sum of cubes formula. A sum of squares does not factor. So if we see a sum of squares, that does not factor. Okay, So where we use these common formulas is when we're factoring expressions with two terms. There's two general steps to do that. First, you factor out any common terms. And then the second step is, well, you use the common formulas if possible on what's left over. So let's do some examples. So I want to factor this expression. So first, are there any common terms, something that evenly divides both of these things? And for this one, no, there isn't. So then I try to use some of my common formulas. And I notice that, well, both of these things are perfect squares. I got something squared minus something squared. So what squared is 16x to the 2? Well, it's 4x. And then what squared is 25y to the 2? Well, it's 5y. So now I'm going to use my difference of squares formula, which says, okay, I should get something minus something, and then something plus something. Where now instead of x's in the first spot, I have 4x in my problem. So I'm going to be writing 4x first. And then instead of just y's in the other spot, I now have 5y getting squared. And 5y should get plugged in. So 4x minus 5y, and then 4x plus 5y. Technically, I should now look at each of these parentheses to see, well, do they factor further? We've already said there were no common terms initially at the beginning, so there still aren't in either one of these parentheses. Like if I just look at these two terms, nothing's common to them. If I just look at these two terms, nothing's common to them. And moreover, each of these parentheses, they're not perfect squares, they're not perfect cubes. That's as far as I can take it. All right, let's do the next example. All right, so first step is factor out anything common. So I noticed that with the 32 and the 50, 2 divides both of those. So I can factor out a 2. And then also a y is common to both of these. So I can factor out y. And when I do that, that leaves me with, well, 32 divided by 2 is 16. And when I factor out the y, that'll still leave me with that x squared. From the second term, the 50 divided by 2 is 25. So minus 25. And then if I divide y to the 9 by this y that I factored out, that still leaves me with 8 of them. So y to the 8. So I'm left over with something very similar to what I had in the previous problem. And I know in the previous problem, well, this first part was just 4x getting squared. It is a perfect square. And then I got minus, well, the 25y to the 8. Oh, that is a perfect square. Because I'm going to have a 5. But then I have a y to the 4th. Because when I square that, I get this power to a power, which means I multiply the powers. Ooh, so I can do some difference of squares there. So I'll get 2y factored out already. And then the first thing, 4x, minus the second thing, 5y to the 4th, times the first thing, 4x, plus the second thing, 5y to the 4th. Okay, so I did my difference of squares. I should ask myself, can either of these parentheses get factored more? Well, I notice 4 is a perfect square, but x is not, so this first term is not a perfect square. It's also definitely not a perfect cube, so I can't really do any of my formulas here. And for a similar reason, I won't be able to do any of my formulas there, because this 4x is not a perfect square or a perfect cube. That's as far as I can take it. Okay, let's flip the page. Let's do a couple more examples. So for this next one, 27t to the 6th minus 8, I want to first give you a chance to pause it and to try this on your own. Remember, the first step is to think about, are there any common terms you can factor out? After you do that, then see if you can use one of the common formulas. So I want to have you pause it and try this for 3 minutes. So pause it and try it in 3, 2, 1, pause it and try it. Okay, so hopefully you did that. Hopefully you paused it and tried it. So this one, they do not have any common terms that I can take out, but we do have some perfect cubes. Both of these are perfect cubes because 8 is 2 cubed. And this first term would be, I need a 3 and then a t squared, right? Because when I cube that t squared, the powers multiply and I get t to the 6th. So I do get some perfect cubes. So the subtraction means it's a difference of cubes. So let me just remind myself what my difference of cubes formula is. It'll factor as like the first thing minus the second thing, and then times the first thing squared plus xy plus y squared. I don't need to write this down, but I'm just writing it down just so I can practice it and better remember it. So now I'm going to be plugging in. So my first thing here is 3t squared minus my second thing is 2. And then for the second parentheses, I'll get that 3t squared now is going to get squared plus x times y will give me 3t squared times 2 plus y squared. That'll give me 2 getting squared. Okay. The first parentheses just stays as it is, 3t squared minus 2. And the second one, when I square this first term, I get 9t to the fourth. Multiplying these two together, I get 6t squared. 6t squared, and then 2 squared, that becomes 4. Okay, it turns out when you do difference of cubes or sum of cubes, the second parentheses, the one that's got these 3 terms, pretty much never factors more. So I don't need to try. But the first parentheses sometimes does factor more. So I should see, okay, can I use one of my common formulas on this? And although t squared is a perfect square, the 3 is not. So the 3t squared collectively won't be a perfect square. Also, 2 is not a perfect square or a perfect cube. And the first part's not a perfect cube either. So none of the formulas will apply to that parentheses. That's as far as I can take it. Okay, let's end the video with one final example, which maybe at first glance looks longer and more complicated, but we can handle this. We just gotta be careful and take our strategies step by step. So the first thing I want to notice is, well, I got 18 times this parentheses thing times that parentheses thing. And then I got a minus sign. And then I got 8 times this parentheses thing times this parentheses thing. So all of these portions that are kind of getting multiplied together, that's one term. Then I got the subtraction symbol. And then all of these things getting multiplied together, well, that's considered to be another term. So that's why this is still a 2-term expression. So first step is factor anything that's common out. And the 18 and the 8, those coefficients can both get divided by 2. Then I notice they both have this negative 2x plus 1 in common. So I can take out negative 2x plus 1 to the smaller power, to the third, because there's 4 of them here, there's 3 of them there. So both of the groups definitely have at least 3. And then with the 8 plus 3x, I can factor out 8 plus 3x to the 5, the smaller power. So those are the common factors. And then I start a parentheses, and then I write what's left over. So from this first group, this first term, well, when you divide 18 by that 2 you factored out, you're left with a 9. So there were 4 of these negative 2x plus 1s, but we took out 3 of them, so that still leaves me with 1, just a negative 2x plus 1. There were 5 of the 8 plus 3x's. I took out all 5 from this first group, so that doesn't leave me with any of them. So for the first group, that is it for the leftovers. Now I move on to the second group. Okay, I'm going to give myself some room, and then I'll close the parentheses later, because I still need to write the leftovers from this second term. Well, when you factor 2 out of that negative 8, if you divide, you'll be left with a minus 4. And then there were 6 of the 8 plus 3x's. I took out 5, so that still leaves me with 1, 8 plus 3x. And then there were 3 of these negative 2x plus 1s. We took out all 3 of them, so there are no more negative 2x plus 1s left over in this second group. Okay, so we factored out all the common terms. What's left is all these leftovers within the parentheses, which I can simplify. So if we distribute the 9, I'll get negative 18x plus 9. And distribute the minus 4, we'll get negative 32 minus 12x. Oh, now there's some like terms I can combine. Because negative 18x minus 12x, that becomes negative 30x. And then 9 minus 32, that becomes negative 23. Okay, so we have the stuff in the front. 2 times negative 2x plus 1 getting cubed times 8 plus 3x to the 5th. And then all these leftovers just simplified to negative 30x sorry, and then minus 23. I should ask myself, well, okay, do these leftovers, do they simplify further? Well, there's nothing in common to each of these terms I can factor out, and neither of these terms are perfect squares or perfect cubes, so that's as far as I can take it with that. And I want to notice something about this, which is what I have now looks like this 2 times this parentheses times this parentheses times this parentheses. So all of these things are getting multiplied together, which is what I need for it to be factored. Whereas what I started with, even though I had a bit of multiplication here, well, then I was subtracting everything that came after that. So this subtraction, the fact I was subtracting those two terms or those two groups, meant it wasn't factored. Okay, so this is as far as I can take it, and that's my answer.